thanks a lot for having me here and giving me the floor for presenting our results. And yeah, I give you will follow the following agenda. So first, we want to explain why did we have to do safe.trAIn? What were the requirements? What is about the ODD? We had the discussion about it in the last call a little bit. Then we looked into the safety concerns and the strategy of the safety case. Then I'll dig a little bit into the architecture, design, and prototypical implementation topic. Then we have a look at the virtual test field, and then we come to the summary and outlook. Okay. Why did we start the safe.trAIn project? And safe.trAIn wants to reach a fully automated train operation, and that would result in a significant reduction of CO2 emissions because it supports a shift from individual to public transport. Why would this be the case? We would have a chance to overcome a considerable shortage of the train drivers, as we see now, especially in Germany. We would be able to reduce the unproductive times from the train driver because, for example, the path from the train driver to the train and back will no more be necessary. You will see in the following slides that the train driver does not disappear. He has another function and he has another working place. Then we would be able to densify the timetable. For example, we could split vehicles that would otherwise run in multi-traction in separate trains. For example, if we are in a typical scenario for the S-Bahn in a big city, then in the regions outside, in the surrounding of the city, you have quite a sufficient capacity in the infrastructure. But due to the shortage of the train driver, then you typically run the trains in multi-traction, so that 3 trains that in principle could run separately run then combined, for example, in a 20 minutes schedule. If you would have the possibility of automated train operation without the driver on board, then you would be able to run these 3 trains separately. So you would have, after every 7 minutes, a train. And that may change then how the people use the public transport, and such we think that we could give a strong contribution to it. And it would also enable us to have multiple trains also out of the central high traffic time frames. And if we get rid of the connection that the driver has to be on the train every time, then we increase the flexibility of the timetable design. And also that will reduce cost and will also add more connections to the timetable. And we will be also able for fast achievements of normal operation in the event of malfunctions, because the replacement vehicles would be able to provide them more rapidly at the position where they are really required. So let's look where our train driver is. So the train driver, you see here, the train, the setup, and also the split between onboard and the track side. So the train driver would then be on the track side and would there support as a remote driver in emergency cases or in special situations. So such a train driver could control a bigger number of trains, and he would not have the problem that he would be always on side of the train. So the most time the train would then run in automatic driverless operation, and in some dedicated times, then the remote driver will connect to the train. So this is the general setup. And for our application, now let's look a little bit deeper into the project scope from safe.trAIn. So we want to develop a safe AI for driverless regional trains. And we want to do it in an integrated development of the guidelines, methods, and the safety assurance of an AI-based obstacle detection systems in fully automated regional trains. And we wanted to separate three important functions. On one hand, the development of safe AI-based functions. The second aspect are the guidelines, the concepts, and the architectures to enable the certifications, and then the proof of all in a virtual test field. So we have then our AI components. We have also the different matrices that check then the function of those components and bring then the evidence that we need for our safety case. It all should be then in readiness level of 4 to 6. And so it's a prototype in the virtual test field in simulation. So the project did start in January 2022. It was funding by the German Bundesministerium für Wirtschaft und Klima, and was also funded by the European Union. And we finished the project end of March this year. The overall budget were 23 million, and you see here that we had quite big scope of different partners, reaching from research institutes to small and medium-sized companies that were also contributing as enablers, and as well as the TÜV organization. So we had also safety assessors that then afterwards did look on our results. And we also then received an report about the general approach. Okay, so let's look deeper in the structure. And on the left side, you see the challenges that we see in the field in the railway domain if you want to apply AI. So there are no safety standards for AI-based perception systems in the railway domain. In the software standards, there is stated that it's not recommended to use AI for safety-related systems. So it's, according to that, a bit also an uphill battle, because the recommendation not to do it in such a way, at least not according to software safety standards in our domain. And there are also have been very unclear requirements for the assessment of artificial intelligence, and there were no established tools and processes. So somehow we had similar goals compared to coherence.ai, but we are much more focused on one application examples. Okay, so we wanted to build a safety enabling architecture. Look there on the different architecture patterns. Then we developed the different matrices and KPIs for the evaluation of the system. And we also did set up a safety case and a testing environment to get quantitative evaluation from our so-called virtual test field. Some of the results then are now transferred to the standardization. We will see that some of the results are, for example, now in DIN spec standards available. We did also a bit discussed about the operation design domain, but first let's come to the safety requirements that we have to fulfill. On one side, we have to take care about the safety of the passengers in the train. So this is the requirements for the large obstacle detections, because if there are large obstacles, the train may run into it and may derail, and due to this derailment, there may be then a threat to the life and healthiness of the people inside the train. The other big issue is the safety from the persons on the track. Quite often, most of the people that are on the track are not allowed to be there because it's forbidden to be on the track, but there are also some rail workers that are allowed and on the track, and we have to detect them and we have to take care that we do not harm them with the approaching train. So one of the big issues was how to find the safety target, and how does the safety target, on the one hand, then is related to the performance measures that we know from the neural networks and machine learning systems. So the overall goal and approach was that our safety target was we want to be overall as good as the driver. And that's according to the common safety methods, risk assessment, and so the detection of the obstacles in our field is quite rare, and the really potential harmful situation is less than once of an operational year from a train. And according that, it is possible that we then argue with a probability of failure on demand, and we decided to take this PFD of 1%, and that's somehow maps to a SIL2. And there was a basis from the ATRASS project and other projects, also some results from Tower also went in the same direction. And so that is the safety goal that was then defined. Then the requirements have to be mapped to the performance matrices in the machine learning domain, and there this maps to the recall, because then we see how often these potential obstacle is detected from all of the different obstacles that are available. So we would have then to detect 99% of the obstacles that are also detected, would also be detected by the train driver. There might be then 1% worse, and in the other cases, then we have to overcompensate this. And so this means that we these have to be the true positives that have to be detected from the relevant elements. But it's not sufficient, because we have to take care that only those persons are counted that are really on the track or near the track, so that they either be harmed or may be harmful for the passengers of the train. So we come now to the operational design domain. It's quite important to define it, and we tried to define it in the same way as it was defined also in the automotive domain. So we tried to keep as close as possible to the existing standards there, and it integrated then the scenery, the environmental conditions, and the dynamic elements, and that also perfectly fit to our situation. And so we have to define the operation design domain in depth, and also the density distribution of the different dimensions from the operational design domain in our application field and dependent from the application field. You see here, these are the potential dynamic elements like the persons on the track or some large obstacles on the track, or here you see the environment from the scenery. So the ODD description is then based on the taxonomy, and it is based for a specific system application scenario. And the taxonomy, for example, is also important for the labeling. So the description of the operational design domain has to be perfectly aligned with the annotation of the data. Any change in there of the semantics will lead to problems in order to achieve the high quality requirements that we have to fulfill. And this operational design domain is then one of the central sources for the development of the architecture, the safety case, the collection of the training and test and validation data for the verification and validation process, and also for the monitoring of the system. All of that has to be set up with high good traceability and consistency. Okay, let's look into the safety case strategy. So why is this challenging? On the one hand, artificial intelligence and machine learning systems are often named black box and are also black boxes. So how to deal with them? Then we are dealing in a dynamic open environment, and we have the problem of the lack of specifications. Then we have to do the benchmark performance from the system related to the safety requirement, and they have to overcome the problem that no standards are available. So we did also deep research on the existing standards, and where we can find helpful advice for setting up the systems. And the overall problem is the uncertainty that you have to deal with. The uncertainty about the correct definition of the operational design domain, the uncertainty of the detectors from one hand, from the sensors. Could a sensor really acquire the information that is required, that is necessary for the classification of the task? Then if you have a neural network classifier, what is the importance, what is the performance of the classifier? Does it really bring the required performance in all of the different situations? What about the rare cases? And for example, also the robustness. So one important aspect where we dig deeper in was then to look in the so-called AI safety concerns that we have to address. So we did deep literature research and tried to identify that was what is available there, and found and identified then the following set of AI safety concerns that we have to address from our point of view also in the safety case. Those you have to address throughout the complete project and complete process, starting from the definition of the operational design domain, then over the architecture that you defined. You have to take care about it during the collection of the data, and also in the verification and validation process. So let's dig a bit more into those marked AI concerns. I want to give you some examples. So first and important, you may have an adequate specification of the operational design domain. In this case here, you may see water on the track, and you have to take care that is also part of your validation, even it's somehow a rare case in your environment. Here, this small robot had the problem that those stairs seemed not to be in his operational design domain, so he did fail and fall in the water here, resulting in a fatal error for this robot. And another problem is that you have to take care about the context if you do the labeling. Here, this object was classified as a tiger, but it's only a dog, and you have to take care about the context that from the shadow is only this structure is seen here on this dog, and so it looks like it is a tiger. Another problem that we quite often see is according the correct labeling and complete labeling. In this scenery, if you try to do a correct labeling of the different persons, you see how hard it might be if you do it. And the problem is, if there are persons then on the images that are not labeled at all, then you have examples of a background that should not be trained as a person. So somehow these persons that may look like those persons that were accidentally not labeled may not be detected afterwards from your system. And that is really one big issue, that the labeling quality must be much better than the intended precision of the system that you want to build, because there are other errors also coming into play, and so the labeling performance must be extremely high. Then you have the problem of the untrustworthy data sources. Here is an example so that you have issues of information in the images, for example, from the image source, and it might be then much simpler to read this text than to detect the horse on the image. And that may then result to problems, but also, for example, if the some persons on the data set were not correctly labeled for detection of persons, then you may also result in a less performance of your classifier. And also that is a really big problem. On the next slide, here we look deeper into the issue of the reliability in corner cases. So this transporter lost the tomato on the street, and under these circumstances, for example, the braking distance may be increased. And this might not have been in your operational design domain, not in the validation, and you have to think how to deal with such problems, how to identify those out of operational design domain detection issues. Here it's the image from the General Motors from the cruise case. It cannot see it on the image here, but that was a problem that in a rare event, due to another accident, a person was thrown in front or near the cruise car. And this event that not the car directly had a collision with a person, but the person was somehow flying through the air and then landed in front of the cruise car, was not really part of the operation design domain, and thus resulted in the problems that the system reacted in the wrong way according to the situation. It tried to drive away from the situation, but harmed due to that the person that was laying then on the street. Here, another use case from a situation. So the system was trained on cyclists and on people walking on the street, but the combination that somebody was pushing a bike was not detected and classified in the right way. So the pushing of the bike, in this case also, that is the famous Uber case, was also not integrated in the correct way in the operation design domain of the system. Here, another example from Waymo crash, and I think it's also cruise. Where the car did follow a bus, but this bus was longer. It was a bus that was extended and could move the front and the back path, and was longer than the specification. And such the car did follow the beginning of the bus and not the end of the bus. And so it underestimated the distance from the bus, because in its model it was defined that the maximal length of a bus is dedicated, and it crashed into the bus, even the LiDAR system was available. Here we can see that the lack of robustness is also a problem. So, for example, this invisible cloak today looks different than from the Harry Potter time, because just due to something printed on this cloak avoids that it is detected then by the neural network. So this is something that we would put into the lack of robustness topic. Also, another problem here, also quite famous, is the speed limit sign that was interpreted in the wrong way, not as 35 miles speed limit, but 85 miles speed limit. Another issue is the data drift. If you see how the clothing changes, or if suddenly the people are wearing masks due to the corona diseases. That may be distinguished then from the concept drift. The concept of a moving person did change, because the person was standing here on the e-scooter, and it was moving, so the concept of a standing person or moving person to change. Also, that we have to take care about those issues. We have to take care when we define our systems and when we define our out of domain detection or out of distribution detection systems. So if we have one of these AI safety concerns, then we have to decomposition it, have to identify different aspects and how these AI safety concerns may appear in our domain. And then we have to look to the AI life cycle, and then have to check, okay, in which part of the life cycle do we have to take care about this issue? And then that results then in the so-called landscape of AI concerns. It's a table where you have, on the one hand, the safety concern, on the other dimension, then the AI life cycle, and then you have different activities that you have to do during the system development in order to guarantee and to avoid that this safety concerns brings harm to the system and to the persons that you have to protect. Another thing was then we did set up the architecture, and as well on the component level, as well on the system level, we did the typical failure mode and effect analysis to identify what are potential risks that show up, and to understand the failures, and also to then derive strategies in order to avoid then risk coming out of these aspects. So we did their analysis for the camera, clocks, mid-level fusion, high-level fusion, track detection, as well as on the system level. And then we somehow developed monitors and integrated them to the system architecture so that we could provide evidence that we can deal with those problems and those failures that may arise either on the different components or on the system level. This then we went over to the safety case strategy that has 5 pillars. So on the one hand, we have processes that are tailored and applied to the specific perception use cases and to the special requirements of our system. The next column is then that we make an analysis of the non-conventional redundancies in our safety architecture. So one of the major principles of the architecture is that we apply diverse redundancy in order to overcome the systems. For example, the use of a camera, a LiDAR, and a radar sensor is in this sense a diverse redundancy because we have different sensors that use different physical effects in order to detect then collect data that enables us to detect then the objects on the track. And another non-conventional redundancy, for example, are the combination of different machine learning based detectors or conventional implemented detectors in order to provide then sufficient performance for our designed for our goal defined by the probability failure on demand from 1%. Another important issue is that turns a little bit against the really black box systems that we identified that we need sufficient understanding of the causalities of the functional behavior. And that comes from different aspects, because the more you know about the system, the less you have to do on the right wing on the validation part. So if you don't know much of how your system works, then you have to put much more effort on the right wing for the validation. And the better you understand your system, the better you can, for example, give arguments that the system is really working on causalities and not on correlation, like the clever Hans effect. Then we have to test with real and simulated data in our virtual test field, because it is really rare the person is on the track during the normal operation hours of a train, and thus we would not expect to have sufficient validation data. So that's also special and different from automotive domain, that we also for the validation will need some simulated data for the validation of the system. The next pillar is then the safety monitoring, doing the operation, for example, the out of distribution detection or out of domain detection aspect. Now we come to the architecture. So as I said, we developed an architecture that is based on diverse redundancy. We started with a high-level architecture from the JDL pattern from the Joint Directors of Laboratories. We then built up the complete architecture in a SysML notation, providing there then also the traceability from the requirements to the system setup, and have a complete documentation according to the V model. And we integrated there also then the results from the systematic system level FMEA and component level FMEA. So typically the countermeasures for those failures are then components that are, for example, as monitors, identify if some of the failures appears, so that we can avoid then the risks for the system performance. So that was then done to a systematic dialogue with the technical expert to also select the applicable and adequate AI components for the detectors as well as the non-AI components. This is the overall architecture that we have here, the different sensors that then put the information into the scene that we set up. Then we have components that analyze the scene and then assess the situation. And here is the monitor that takes then care about the overall system performance, like system health monitor. You see here the different approaches that we used. For example, LiDAR and camera systems. And then for the LiDAR information, we applied as well non-AI object detectors as well as AI-based object detectors. And also for the camera, then we also used different types of AA-based, for example, pedestrian or large object detectors. This information then goes into the fusion, is then combined with a track detector and a localization, and that then gives in the information to the obstacle determination and handler. So the analysis of the capability from the different sensor types as well as detector types did then include the functional performance, the safety realization, the operational coverage of our domain and the robustness, and the possibilities about error detection and mitigation capabilities. And we then did build up a powerful combination of different sensors to be able to achieve the performance, the interpretability requirements, and determinism. So we have here some examples for the panoptic pedestrian detection. And on the next slide, we have here video from the track detection module. So it is important to identify the clearance space, and only those objects that we detect inside this clearance space are then safety relevant, and only those have then to be taken into account if we evaluate then our probability on failure on demand. You see here then the integration from the 2 detection, 3D hypothesis, and then the integration in our 3D representation of the scenery in front of our train. Then we come to our virtual test field. This virtual test field has then to support the safety argumentation. It has to enable an efficient verification of the requirements and to have to support then our minimal viable product development through an early feedback. So we defined different test levels. We combined diverse test methods and our test system architecture, and it's also based on MLOps and cyclic validation process in order to detect the errors early. We had then the test management environment for the traceability of all those different aspects. So I want to show you one example of a test scenario and test data that we then tested on the so-called Havelländische Eisenbahn. There we had the possibility to set up scenarios, and also these scenarios are somehow a simulation because these are not real persons. It's a train then approaching them, but not with the real speed. And here, this is a large object emulation like a car. And so we have different scenarios, and then we see here that we approach the persons, the mannequins with different speed. You see here then the description of the operational design domain. You see here the requirements that we test, and the combination of them then results in this scenario for the test case. Okay, so we had quite a lot of tests, a lot of presentations. We have developed several DIN standards that came out from our project. And there are two major outputs. So we provided different DIN specs that are the DIN spec 99002 for the AI terminology in the railway sector that is published. Another DIN spec 99004, it's for the definition of the operational design domain in the railway domain. We also did put our definition from the architecture in the so-called ERJU R2DATO project. That's a European project that is done with in cooperation with different operators and suppliers from the railway sector. And so the basic perception architecture was also there accepted then to get into the future standard with some smaller modifications. And then we identified major AI relevant concerns. They were published. Also, the AI landscape was published, and with several other things. We also published our safe MLOps process, several concepts to take care about the data quality, and also some aspects from our validation concept. And that goes then in some part to the information, to the sector, and also to follow-up projects and towards products. So what is the outcome from our point of view? We now know what we have to do and how. We have not achieved the required performance. We were not able to provide sufficient evidence for those requirements, so there is still a lot to do. But you see here the results that we have achieved, and we have now a much better alignment, especially between the safety and AI community. So it's we have the feeling we are on the right way, and we have to continue our journey. So thank you for your attention, and I'm looking forward towards your questions.
Thank you, Thomas. Maybe you can also stop sharing. Yes, I see some people are very happy. So if I understood well, please raise your hand for questions. If I understand well, in your simulated test case, the speed is 25 kilometers per hour?
Yeah, because that's at the half HVLE where we tested, yeah, there is a maximum speed limit. And also that limited, and that is the reason. And also we have always to stop in front of our monikers because we do not want to destroy them. They are expensive. And so these are the restrictions, and I want to take it also as an example for simulation. So quite often if we discuss with the people, they just think about the simulation that you do with Omniverse or something like that, but also these aspects, how you, for example, we also name it Hollywood, yeah, because you have some actors and you put up a scenery, and with this scenery, then you try to check the performance of the system.
So let me just go on with my question before leaving the room to Maximilian and Sarah. Of course, if you have to see far away, and especially if there are turns, it's completely impossible to see anything. Yeah. So have you thought of solutions for, yes, a long distance analysis of situations, or you just worry about these cases where you go slowly and you need to only to see 200 meters away?
Yeah, we did think about the complete set of use cases. And that is the reason why we argue that we have to compare with the performance of the existing train driver. Also, the existing train driver is not able to look around the corners. He's also not able to see everything during the night, and it is accepted. So it's a huge difference between the automotive domain and the railway domain. We run our service even if we cannot detect all the obstacles that are in our braking distance. And that is accepted, and that is how our railway business is run.
Okay.
And so that's the major aspect is, and the comparison is, how good is the train driver? And we know that the train driver also does not detect every obstacle that is in 600 meters. The problem is about the assessment from the train driver, and what can he see, and that is the goal that we have to achieve.
Okay, very clear. Maximilian?
Yes, thanks a lot for the great presentation. I liked it very much. My question goes in a similar direction as part of your last answer. So to what extent can you transfer the results of safe.trAIn to other domains like automotive, for example, or maybe even using AI for medical products?
I think the landscape of AI concerns is general. There's, from our point of view, nothing special in. I think also the safety case strategy may also be overtaken. There may be differences in the amount of understanding that is required. So in our domain, the safety people and the Eisenbahnbundesamt and so on, they're extremely conservative. We have no experience, not a lot of experience with assistance systems and so on. So I see there a huge difference in the approach and in the requirements that we have to fulfill. But I think it's okay to have this requirement because it's a really important topic. So we have to know and understand how the system is working. We also have the opinion that it is maybe depend on strongly on the system architecture that you have. For example, if you have a track detection system that is AI based, but where you are able, for example, from the localization and with the map, you can then detect that your track segmentation is wrong because it differs from that one that comes from the map. If you are then able to argue and to prove, bring the evidence that you may detect all of those errors, you have to put other requirements to such a track detection system than to a system where you have to detect the objects on the track, where you may not have the same possibility to somehow cover the possible errors of the system. And then it also may depend, for example, if you have different parallel diverse detectors. How strong can you argue that you don't have common errors? And the stronger your argument is that you can avoid these common failures, the stronger then, well, the less are the requirements then also a bit to the explainability of the system. So it's strongly dependent how your architecture is built, how you may detect other problems in the situation. Yeah. Does it give some answers?
Yes. Yes. Thank you.
Sarah?
Yes, hi. Thank you for the presentation. Thank you very much. Full disclosure, I used to work on the TWIN project financed by the French government for the 1 kilometer object detection for the train. And before my question, you might be interested to know that we actually did a comparison with the performances of train drivers. And in the daytime, they were always better than any algorithm we found. We found that they were super detectors because apparently because they drive the same trains every day, they know the rails very well. And so they're actually excellent at detecting small variations from very far ahead. So we couldn't beat them with an algorithm during the daytime. Obviously, at night, it's very different. But one of the big thing that stopped us when we did that, it was 4 years back for us, was with the certification authorities, we couldn't go over the granularity of the OOD. Like we defined an OOD, and then they were like, okay, so we had to go from 0 to 90 kilometers per hour and cover all the environmental conditions. But in the end, it was too many possible cases for us to handle. So I was wondering how you, for example, all the different, we had a granularity for the angles of the sun. We set it at, I don't know, I think it was 30 degrees at the time, plus the speed, the vibration of the motor and everything, and all the weather conditions. It just was too much for us. And we didn't have images representing all these cases that we could test on. And we offered synthetic images. It was rejected by the authorities because we had to prove that they were good enough. So, right, really, I was wondering, how did you deal with that?
So we have also no improvements till you are addressing very important and very hard challenges that we have here. We may not need if we try to build categories for all aspects of the operational design domain. It may lead to more difficulties than if we think about density distributions over those examples and multi density distributions. It may a bit help out there, and then we have to agree on the sampling number how we do, and so that might be a way we come out of those problems for the discussion. We also try to work now to standardize the operational design domain on the European level. Right. So the hope is somehow if we at least achieve to define such an operational design domain that is accepted by the at least by the operators and chain builders and providers of such systems, it somehow may help in the argumentation, and also may help
Yes.
that we have at least a better argument that quite a lot of experts in the field looked on it and somehow helped that it is to some extent complete. It makes sense.
Okay, because we got the argument back from the security offices who are definitely not into AI, and they said, well, this is the way we have to certify traditional systems, and we have to know it works if there's like thunder going or something. So you have to prove that you work in those cases. And to your point of the distribution, this is very much to the tail end of the distribution, so that's not very easy.
Yeah.
And so okay, so I hope you managed to convince them. Really
Yeah.
hope.
It's hard work, and it also then depends somehow to restrict it. So we have together with Deutsche Bahn another project that is then more dealing with the depot and stabling area. And if you look at this, then you may have a much better, more restricted operational design domain, because the speed is lower and the area may be fenced. You know much better about the people that are there. You know more about the cooperation of the people who are on the track, and you may have additional other arguments that you may feed in. Yeah? And if there is a thunderstorm, then, for example, the remote operator must drive the train. Yeah. Otherwise,
Yes.
they have to be stopped. And so also you may somehow play with the operational conditions that you use.
Okay, yes, thank you very much for your answer and your presentation.
You're welcome.
Yeah, I have a last question about the methodology, because you might remember that in Confidence.ai, we also developed a methodology. And in one of your slides, you talk about the methodology, but I didn't really keep track of all the details. So you know that we developed a methodology, which is, by the way, available on the website, on the book of knowledge, Confidence.ai. And since you have also a methodology, I think it would be really interesting to compare. And so I don't know if we can have the reference, or if there's a published version of the methodology which is readable, at least not in German for many people. And then one of the things that we think of doing, but not this year, I think it's too early, is to come to try to develop a standard for AI engineering for critical systems. So the methodology is part of that. And so maybe sooner or later, we could also work towards, let's say, when comparing, taking the best of each and developing some kind of proposal for a standard on the methodology to develop AI systems for critical applications.
Yeah. We did not disclose the methodology completely. We only disclose some aspects of it, because some of them we see as an intellectual property, and from Siemens and our partners. And but I think it's completely the right way. What we try to put also the knowledge that we have about safety AI concerns also in the risk catalog from the risk management that is used to implement the AI Act. So
yes, I'm part of that, you know.
Yeah. And that would be, from my point of view, helpful to have a set of those concerns, so that we have a list, and so that we can hold on something and say something a little bit like the UL 4600, yeah, from Phil Copeland and partners and other contributors, so that we know, okay, these in more detail are the concerns that we have to address. If we then would also define a set of activities where we could say, okay, if you are compliant to that, this is the state of the art that you have to do.